Hi everyone, I'm Akhil Goyal, Principal Engineer at Marvell. I also work as Crypto Subtree Maintainer for DPDK. In this session, I, along with Anoob Joseph, would be discussing on what is TLS and how we can accelerate it using DPDK. So here's the agenda for the session. We'll briefly discuss on what is TLS and what are its different layers. After that, we'll discuss on TLS handshake and TLS record protocol and how we can use DPDK to accelerate the protocol processing. In the end, we would share the current status which is available in DPDK. TLS stands for Transport Layer Security, which is used for encrypting the communication between web applications and servers. In DPDK, we supported IPsec at layer 3, MACsec at layer 2. Now for layer 4 security, TLS is also added. So what is TLS? It is a reliable layer 4 security protocol which provides end-to-end security channel for data to be sent between applications over the internet. It ensures that eavesdroppers and hackers are unable to see what we transmit, which is particularly useful for private and sensitive information such as passwords, credit card information, and personal correspondence. TLS has basically evolved from secure socket layer or the SSL. TLS has various versions. First version was introduced in 1999, which had many issues. TLS 1.2 was introduced in 2015 after SSL 3.0 was deprecated. Currently, TLS 1.3 is the latest version, which is considered as the most secure version. There are three primary features of TLS. First is the authentication of server. It ensures that the parties exchanging information are who they claim to be. Second is channel confidentiality. It encrypts the data being transferred from third parties to ensure that channel is confidential. Message. It verifies that the data has not been forged or tampered with. TLS is implemented on top of TCP. Hence, it assumes all the features of TCP along with security. Now, there is another protocol added which runs over UDP, the DTLS, Datagram DTLS. There are few fundamental differences between the TLS and the DTLS, while the purpose of both is to provide security at layer 4. As TLS is based on TCP, it ensures ordered packet delivery, while in case of DTLS, out-of-order delivery is allowed. An explicit sequence number is added in the DTLS header to help application handle the out-of-order packets, while in case of TLS, sender and receiver updates an implicit sequence number in the session atomically. In case of TLS, a decryption failure will result in termination of connection, while in case of DTLS, timers are added for retransmission to handle packet loss. Anti-replay checks are also added in DTLS to prevent replay attacks, similar to what we use in case of IPsec. Since TCP can handle large fragments, TLS may generate packets up to 16 kilobytes, while in DTLS recommends path MTU discovery to prevent fragmentation. Now we will discuss on different layers of TLS protocol. Every TLS or DTLS packet is basically considered as a TLS record. The TLS records can be of four message types. First is handshake message, change cipherspec message, alert message, and the application layer data. TLS basically has two subprotocols, TLS handshake protocol and TLS record protocol. We'll discuss the details of both of these in upcoming slides. In case of TLS handshake protocol, handshake messages and chain cipherspec messages are used. Handshake messages are required to negotiate various session parameters like algorithms, keys, etc. Chain cipherspec is used to specify migration to a new protocol protection suite. Now, once the handshake is established, alert and application layer messages can be sent. Alert messages are basically used to signal errors, and the application layer data is the generic data. Now we'll discuss the details of TLS handshake protocol. Since TLS is a communication between a server and a client, we need to have a handshake or a negotiation between them. The handshake protocol basically addresses four major requirements which is needed to have a reliable connection between the server and the client. First is to specify which version of TLS or DTLS will be used and decide which cipher suits and algorithms are compatible between them. Second is the key establishment using public key exchange algorithms. Third is to authenticate the identity of the server using the server's public key and SSL certificate authority's digital signature. Fourth is the generation of symmetric session keys to use after the handshake is complete for the generic application layer data. Various versions of TLS and DTLS have different changes with respect to handshake. We'll not go in details of every handshake process. For illustration, we have taken TLS 1.3 to show the handshake process. Here, the handshake can be considered as a three-phase process. The key exchange process, getting the server parameters, and the authentication messages. In the key exchange phase, the server sends the client hello message, which contains a random nonce, its offered protocol versions, a list of symmetric ciphers and hash pairs which it can support, a set of Diffie-Hellman key shares, or a set of pre-shared key labels, or both, if it supports that, and then some additional extensions, if any. The server processes the client hello and determines the appropriate cryptographic parameters for the connection. It then responds with its own server hello, which indicates the negotiated parameters for the connection. The combination of the client hello and the server hello determines the shared keys. The key establishment can be done using ECDHE or the pre-shared keys. The server, in the second phase, the server then sends two messages to establish certain server parameters. The first one is the encrypted extensions. It sends responses to client hello extensions that are not required to determine the cryptographic parameters. The second is the certificate request. It includes certificate-based client authentication parameters. Now, finally, the third phase, client and server exchange authentication messages. The messages sent by server for the certificate of the endpoint and any per certificate extensions. Then a certificate verify message is sent. It is a signature over the entire handshake using the private key corresponding to the public key in the certificate message. And finally, a finish message is sent, which has a MAC message authentication code over the entire handshake. This message provides key confirmation, binds the endpoint's entity to the exchange keys. Upon receiving the server's messages, the client responds with its authentication messages now. At this point, the server is and this handshake is complete between the server and the client, and they can derive the keying material required by the record protocol layer to exchange application layer data protected through authenticated encryption. This flow diagram is taken from the TLS 1.3 RFC specifications. As we discussed about TLS handshake, now we would see how DPDK can help in improving TLS handshake performance. As we learned about TLS handshake, there are multiple operations involved, like creating handshake messages, which application can take few cycles. Now, apart from the creation of messages, all other processing involves cryptographic operations, which if done in core may take a lot of cycles. Like hashing for generating MAC can take around 10 cycles per byte of data. Similarly, symmetric key operations for encryption, which takes around 100 to 1000 cycles per block of data. The key exchange using ECADHE or any other protocol may take around 10K to 100K cycles. The certificate authentication using RSA may take few 100K cycles. Now, DPDK provides RT crypto APIs for both symmetric as well as asymmetric crypto operations, which, depending on software or hardware crypto device, can help in reducing these core cycles. The ECDHE and the RSA are asymmetric crypto operations, while the ciphering and hashing are symmetric. So, depending on the hardware on which the application is running, application can offload these cycle-consuming tasks to cryptographic accelerators. So at the application level, it can form handshake messages and use DPDK crypto APIs to reduce the core cycles required for these operations. As we can see from the previous slide, asymmetric crypto operations are the most cycle-consuming part of the TLS handshake. Even if the handshake happens in the control plane, but still the latency for handshake can be improved using hardware offload drastically. I mean, if it is happening only one time in the communication channel, still the latency can be improved. DPDK currently supports RSA, Diffie-Hellman, ECDH, ECDSA algorithms for key exchange and the certificate authentication. EDDSA is also getting added in 24.11. The patches are available for review on patches. In the future, post-quantum crypto algos are also planned to be added. Now, Anoob would take you through the TLS record protocol and support in DPDK. Thank you.
Hi everyone, I'm Anoob Joseph, Senior Principal Engineer at Marvell Technology. I'm also a co-maintainer of the RT Security Library in DPDK. Now that we have looked at the TLS handshake protocol, thanks to Akhil, let's proceed to the TLS record protocol. TLS record protocol is the one that protects the application data, basically all the data that a client sends to a server and vice versa. Once the TLS handshake is done, client and server will have the same symmetry key, and they can communicate using this key going forward. Here is a sample packet layout of a TLS record. From the top, data can be regular application payload, can be like an HTTPS request or whatever. The processing need not be strictly in this order. I'm just keeping it like this for the demonstration purpose. The TLS header would get added first. The payload data and certain fields from the TLS header would be used to generate the MAC. This is nothing but the digest from auth operation. Then ciphering operation, that is encryption, would be done. At this point, padding could be done, and it is done for two reasons. One is to align to block size when using block ciphers, and second is to hide the packet length of the original packet. Once the padding is done, then the payload could get encrypted. This is the scheme used for block ciphers and varies slightly for other types, which we will see in the next slides. Since TLS is a security protocol, cryptography would be at its core. There are three types of ciphers used: stream ciphers, block ciphers, and AAD ciphers. Stream ciphers are not preferred due to vulnerabilities. Block ciphers and AED ciphers are more common. Block ciphers can be like ASCBC, 3DCBC, etc. for ciphering, and SHA-1 HMAC, etc. for authentication. While it is more secure than stream ciphers, there are still some vulnerabilities and certain inefficiencies with block ciphers. AED ciphers provide both confidentiality and integrity for the encrypted data. ASGCM, ASCCM, Chachapoly, etc. are some of the common algorithms. These are more preferred. In TLS 1.3, which is the latest TLS version, only AED ciphers are supported. That is, no stream ciphers and no block ciphers. Let's start looking at some of the building blocks of a TLS record. As with any security protocol, TLS also has a concept of atomic sequence number. These unique sequence numbers ensure that the cryptographic operations result in a different output each time the operation is performed. If not, usage of the same inputs, that is the same sequence number and the same input data, can result in compromising the symmetry key. With TLS, both the sender and the receiver maintain a sequence number and increment the value synchronously. This means that TLS expects perfect in order delivery, and this is possible since TLS is on top of TCP. So how does DTLS work, which is on top of UDP? UDP doesn't guarantee order delivery of packets, and so DTLS behaves differently. As with TLS, DTLS also assigns atomic sequence number in the sender side and puts a sequence number in the packet. At the receiving side, this sequence number is used for decryption and digest verification, etc. Since the sequence number is put in the packet, it is possible for an attacker to capture few packets and replay it again. So this is known as a replay attack. In case in DTLS, there is a concept of anti-replay checks, which basically is same as what is present in IPsec. This is to prevent the replay attacks. Earlier when we saw this slide, there were asterisks in multiple areas like TLS header and padding, there was asterisks. So there are some specific handling in TLS for these sections, and it is important to understand both these topics to understand some of the API choices. First, we will see padding. For block ciphers, the encryption data needs to be aligned to the block size. Sizes like 8 or 16. With TLS, the data that gets encrypted would be the traffic between a server and a client. It can be like logging into email with HTTPS or bank details, etc. So leaking any information from such a traffic may lead to attacks. Packet sizes can be an indication of certain requests from upper layer, and so TLS allows an implementation to add some extra padding for traffic flow confidentiality. The total padding can be up to 255 only. TLS follows a simple padding scheme where each padded byte will have the length of the padding. This actually limits the max padding to 255. To summarize, we could have extra few bytes of data to be encrypted. If we assume that the data plus MAC is like 33 bytes, then the minimum padding can result in packet to grow to 48 bytes. And if TLS implementation wants to hide the original packet length, it can add some more padding and make the packet size to 64 bytes. Do note that the TLS implementation is expected to verify this padding in receiver side during decryption or TLS read operation. Not verifying this or not verifying the padding can lead to certain kinds of attacks. TLS 1.2 record protocol header is rather simple. It is just 5 bytes and it has just 3 fields. The first one is content type, indicating the content type of the payload. Second field is version to indicate the version of TLS. Then there is length to indicate the length of the packet after encryption. The code snippet here is from the RFC and it specifies how the MAC or digest generation is done. Basically, it needs a key, sequence number, the content type, version, length, and the payload. In the TLS write operation, that is encrypt operation, digest is computed using the plain packet length, but the header would be having the encrypted packet length, which may include padding. At the receiving side, TLS read or decrypt operation would have to do the exact same computation and make sure the MAC is the same. This is the way to ensure that the data was not tampered with during the transmission. The inputs needs to be the same to get back the original MAC. When a packet is received, how can the receiver compute the MAC? So we need the fields that we saw in the previous slide, basically write key, sequence number, then the fields such as type, version, length, and fragment. So the write key is the one that after the TLS handshake, both the client and server will have. So that is okay. Sequence number, again, it is coming from the state. The receiver state will give the sequence number. Then there is type and version, which comes from the TLS header. Following that, there is length. So what is the length that has to be used for the MAC computation? It is the plain text length, while the length field in the TLS header is the encrypted length, which includes a variable padding, which is impossible to predict. So how can we work around this? So there are two solutions. One is perform decryption first and then perform authentication. It works, but the problem is there won't be any chaining. So we have to do the ciphering operation first and then go for the auth operation, which means that there will be like more DMAs when using an external accelerator. The second option is to decrypt the last block, get the padding value, and then perform the chained cipher plus authentication. So this again means multiple passes. First pass is to decrypt the last block, get the original padding, and then use that for the computation of AAD, and then perform the chained operation to decrypt the original packet and authenticate at the same time. So how does DTLS 1.2 compare with TLS 1.2? Crypto operations are similar, just that RC4 is discontinued for DTLS 1.2. Other than that, crypto operations are just the same. As discussed earlier, DTLS need to carry the sequence number since UDP allows out of order delivery. So the packet layout is on the slide and it demonstrates how the sequence number is packed inside the TLS record packet. DTLS also has a concept of epoch, which can be thought of as an upper two bytes of 8-byte sequence number. The actual sequence number in a TLS record is uh, is 6 bytes, but it's better to think of epoch plus sequence number as an 8-byte sequence number. Essentially, when rekeying event happens, epoch gets incremented, and both sender and receiver would need to switch to new epoch. TLS 1.3 is the latest version. It is also on top of TCP, and it is like the newer version of TLS 1.2. It has major changes in handshake and record handling. TLS 1.3 supports only AED ciphers, that is only ASGCM, CCM, and Chachapoli. No block cipher or no stream cipher, and yeah, no associated padding issues. TLS 1.3 allows zero padding, and that can be up to max packet size. Mac generation and verification uses ciphertext length instead of the plain text length to simplify the decryption or TLS read operation. So earlier we discussed about the padding being variable and the requirement to use the plain packet length, complicating the digest verification case. So in case of TLS 1.3, the spec states that the MAC generation is based on the ciphertext length instead of the plain text length. Do note that the differences between TLS 1.2 and TLS 1.3 it can itself be a 1 hour topic. So the ones that are highlighted above are just few ones that impacted some of the DPDK API changes. So how can DPDK help in accelerating TLS record operations? There are two libraries in DPDK which helps in performing parts of TLS record. One is RT crypto library, which enables cryptographic offloads on an RT crypto div, and the other is RT security library, which enables security protocol offloads. RT crypto is designed to perform raw cryptographic operations such as ciphering and authentication. Since RT crypto performs only crypto operations, it is not expected that the packet layout or the length would change following an RT crypto operation. RT Security Library enables protocol offloads. It allows applications to offload crypto as well as protocol operations to an underlying security device. Since it performs protocol operations, the packet layout and the length can change. Basically, it can grow or shrink based on the protocol and the type of operation. Also, it allows for protocol-aware acceleration and optimized paths. Both RT crypto and RT security libraries can accelerate TLS record protocol operations. Leukocyte crypto is the mode where CryptoDev performs only cryptographic operations, while Leukocyte protocol is the one which handles complete protocol. So Leukocyte crypto is the RT crypto library, and Leukocyte protocol is the one is enabled by RT security library. As we saw earlier, atomic sequence number assignment and anti-replay checks are an integral part of TLS record protocol. In case of Leukocyte crypto, application is expected to handle it, while in case of protocol offload, it can be fully offloaded to the security device. Similarly, TLS header additions, IV generation, AAD or additional authentication, data construction, etc. are some of the basic operations that need to be done by the application in case of Lucasade crypto. And in case of RTE security devices with Lucasade protocol, these can be performed by the security device. Padding insertion and verification is another similar task which requires application to go through the data one more time after decryption if you are performing Lucasade crypto. In case of protocol offload, this can be handled in the device, allowing application to not go through the packet again. And finally, we have the ciphering and integrity protection, which can be handled by the crypto dev in case of both Lucasade crypto and Lucasade protocol. Earlier, we had described about calculating the original packet length for digest verification purpose and how it was causing multiple passes and other issues. That can also be optimized in case of Lucasade protocol, as a security device is aware of the protocol and it can very well look at the last block and make such decisions on the fly. This is the transform which configures an RTE security session as a TLS record session. Currently, it supports TLS 1.2, TLS 1.3, and DTLS 1.2. So as we can see that there are fields that are very specific to DTLS 1.2, things like anti-replay window size, epoch, etc. And there are like common configuration, things like lifetime, which is applicable for all the TLS protocols. So all that is captured in this transform. Data path for crypto devices which supports RT security is enabled using standard RT crypto dev APIs. That is RT crypto dev NQburst and DQburst for the data path. As we discussed earlier, TLS record requires some more additional inputs than what was required for other existing offloads such as IPsec. One use case is padding, where an application can request the TLS record protocol to add more padding than the default padding. RT Crypto had a field called aux flags, which we kind of repurposed to allow application to pass this padding info to the security device. Originally, the field was acting as an output from the security device to the application, and we modified it such that it can also be used as an input to the security device. The field also carries as an output information such as soft expiry, which is applicable for TLS record as well. So as an input, applications can give padding information, and as an output, that field can carry the soft expiry notification. Earlier, we saw that there was a field called content type, which was put in the TLS header. But with TLS 1.3, this content type was moved to the encrypted packet data. So the content type in the header was supposed to indicate as a application data, but the actual content type was actually inside the TLS 1.3's encrypted payload. So this was supposed to be inserted between the payload and the padding, and upon in the receiving side, this need to be like after decryption, the padding needs to be determined, like based on from the end, the TLS implementation has to see how many 0 bytes are there, and the last non-zero byte will be counted as the content type. So that field, the content type, also needs to be given back to the application for its processing. So this fields becomes an input for the encryption or the TLS record write operation, and an output from the decryption or TLS record read operation. So there were some reserve bits in RT crypto and we modified the spec to allow a field called param1 which can be implemented per protocol, and this is the one that carries the content type. Currently, we support TLS 1.2, DTLS 1.2, and TLS 1.3 in DPDK. The API changes were introduced in 2311. The unit tests were introduced in 2311, and then subsequently the coverage was increased with every release. Currently, the unit tests cover all the features. There are test cases to test all algorithms with all packet sizes for each protocol, etc. For measuring performance, TLS record is supported with DPDK test crypto perf. It was added in 2403 release. Currently, the feature is supported by Marvell Octeon 10 Crypto PMT. We had a small team from Marvell to introduce TLS record protocol feature. We had contributions from Akash, Akhil, Tejasri, and Vidyasagar. Special mention to Jirin and Umesh, who was also involved in defining the architecture.